Hello students, today we're going to be going over Skill 12, Polynomials and End Behavior. Our objectives for this lesson are that by the end of this lesson, scholars will be able to identify a polynomial, determine the degree of the polynomial in standard form, identify the degree of a polynomial function from a graph, and identify the end behavior of a polynomial graphically and algebraically. If you guys have any questions or you need to pause the video before we can move forward, feel free to do so. And here is our important vocabulary for the lesson. We are going to need to know the definition of a polynomial, the definition of a standard form polynomial, what a leading coefficient is, and the degree of the polynomial. I'm going to give you a few seconds to write these down, and then we'll move on. Okay, so when we talk about identifying polynomials, these are the traits that we're looking for. A polynomial cannot have variables or exponents in the denominators. So if you see something like x to the third in our denominator right here, it is not a polynomial. Polynomials cannot have roots or absolute values. So right here, we know that this is not a polynomial because it has a square root. And polynomials do have whole number exponents. So this right here would make this not a polynomial. This is not a whole number exponent. And we're just going to go over an example real quick. We're going to identify these expressions as polynomials or as not polynomials. Negative 3x squared plus x to the 1/2 power plus 13. X to the 1/2 power is not a whole number exponent. Therefore, this is not a polynomial. Remember that our polynomials have to have whole number exponents. Q to the 5th plus 3q plus 12. This is a polynomial. There's nothing wrong with it. It has whole number exponents. The absolute value of negative t squared plus 13t minus 7, well, polynomials cannot have absolute values, so this is not a polynomial. 0.15s to the third plus 3s minus 4s. This is a polynomial. Just because it has a 0.15s to the third does not mean it is not a polynomial. This is a polynomial. Remember, our coefficient does not affect whether we have a polynomial or not. 4x minus 3y squared plus 17 is a polynomial. Again, a polynomial does not judge whether it has more than one variable. Now we're going to look at the standard form of a polynomial. Standard form of a polynomial is written in descending order. That means from highest degree to lowest degree, starting with the degree of the polynomial, and that is the highest exponent in the polynomial. So here we have negative 12x to the 6th plus 3x to the 5th minus 4x to the 3rd plus x squared plus 36. We can see that our leading coefficient is a negative 12x, because that is what is attached to our degree of our polynomial. And we can write underneath the degree of each of these terms. The degree of x to the 6th is 6. The degree of 3x to the 5th is 5. The degree of negative 4x to the 3rd is 3. The degree of x squared is 2. And the degree of just 36 is 0. And here we can see the names of our polynomials. We define them by their degree of the polynomial. So if our degree is 0, we call that a constant polynomial. This is an example of negative 9. A linear expression would have a degree of 1. That is x minus 4 as an example. The quadratic has a second degree polynomial, and that can be written as x squared plus 3x minus 1 as an example. A cubic polynomial expression has a third degree polynomial. X to the third plus 2x squared plus x plus 1 as an example. A quartic polynomial has a fourth degree, and the leading coefficient could be 2. And we could write that as 2x to the fourth plus x to the third plus 3x squared plus 4x minus 1. And we have a quintic polynomial expression which has a fifth degree of polynomial, and the 7x to the fifth plus x to the fourth minus x to the third plus 3x squared plus 2x minus 1 as an example. if we are naming polynomials by the number of terms, it changes. A monomial has one term, whereas a binomial has two terms. A trinomial has three terms. We see 1, 2, 3. And a polynomial with an x number of terms, we see, for instance, this one has 4. We call it a polynomial with however many terms. So this polynomial has 1, 2, 3, 4. We would call that a polynomial with 4 terms. So to find the polynomial's leading coefficient, we have to find a couple of things. We're first going to have to combine our like terms. We're going to have to rewrite this polynomial in standard form, and then we identify the degree and the leading coefficient, and then we're going to name this polynomial based on the degree and number of terms. Looking at like terms, I see that I have a positive 5 here and a negative 14 here. I can combine that to make a positive or negative 9. I have a negative x here and a positive 7x here, and I can combine those to make a 6x. These other two terms don't combine, so we will have a negative 9 minus 3x6 plus 6x plus 3x squared. And then we're going to rewrite in standard form, and to rewrite in standard form, we're going to have to find our biggest degree, which is right here. And then we're going to write in descending order. So this will be negative 3x to the 6 plus 3x squared plus 6x minus 9. Remember that this is a higher degree than our 6x, so it comes first. We're going to identify the degree and the leading coefficient. Our degree of our polynomial is 6, and our leading coefficient is going to be negative 3. Now, if we were going to name this polynomial based on the degree and the number of terms, this would be a 6th degree polynomial. And we're going to count the terms. We have 1, 2, 3, 4 with 4 terms. Oop, I forgot to add my degree. Right there. My 6th degree polynomial. And this time we were asked to find the leading coefficient of this polynomial, but we're also going to do all of our other steps. So we're going to look for like terms first. I see a positive x on the end here. That will match up very nicely with this negative 31x. None of my other terms are going to combine, so I'm going to have 4x to the 5th minus 30x plus 8x squared minus 19. Then I'm going to rewrite in standard form. I look for my highest degree. It looks like this 5 right here is my highest degree. And then I'm going to rewrite in descending order. So I have my 4x to the 5th. My 8x squared is next. Then I have my negative 30x minus 19. And the degree of my new polynomial expression is 5, and the leading coefficient is a 4. So this would be a quintic, because our degree is 5, polynomial with, we're going to count our terms, 1, 2, 3, 4. So this will be a quintic polynomial with 4 terms. So when we look at identifying polynomial functions graphically, what I mean by that is, we're going to look at what this line is doing as it moves across our graph. And the degree is going to tell us how many changes of direction we have in this function. So if we have a degree of 0, we have just a straight line. This line is not going up, this line is not going down. It's just going straight across. If we have a line that goes diagonally, just a straight line, that is going to tell us that we have a degree of 1 in our equation. Remember, a degree of 1 is something like x minus 1. If we have a degree of 2, what we're going to be looking for, and when we move on from 2 and up, we're going to be looking at the directions that change in our graph. So we have this line that comes in and is moving down, and then at some point it changes directions and it changes to go up. We have 1, 2 changes in direction, and that is a parabola. Those are like x squared. So if we have a degree of 3, remember these are like our cubics, they're x to the thirds. We have a graph that if it is positive will come up at some point as it gets closer to 0, and then it will turn down, and then it will turn back up. So these are the 3 directions that we have, 1, 2, and 3. And we can do the same thing with our 4th degree. So x to the 4th is going to look something like this. We're going to go down, and then we're going to come back up. Go back down right here. This one's very small, and then this one is going to go back up. And remember, these are going up infinitely after this. These arrows continue to move. So if we have something that's like a degree of 6, what that might look like is, if it's positive, we're going to have a 1, 2. Okay, and we can count our changes of directions here. We have 1 right here, and we go back up, that's 2, down, that's 3, up, 4, down, 5, and then this got cut off, but that will be our 6th. So we have 1, 2, 3, 4, 5, 6. So the degree is going to be equal to the number of directions in the function. You can just, if you have trouble figuring out what that means, you can draw your arrows like I do. And when we talk about end behavior of polynomial functions, we are asked to find what is called the SLED. And the SLED is an acronym that stands for the sign of the leading coefficient and the evenness of degree. Let's do an example. So we take our first function, f of x is equal to 4x to the 4th plus 3x to the 3rd. And what we're going to look at is our leading coefficient, which is 4. And that is positive. And our degree, which is 4, and that is even. If we do our second example, we will see that our leading coefficient is -3, which is negative. We can write these down here if you guys would like. And our degree is 8, which is even. Now in our next two, if you look at our functions, they are not in standard form, which means we do not know what our leading coefficient is just yet. If I rewrite them in standard form, which means that I'm writing them in descending order, starting with my highest degree, I can see that my sign of leading coefficient is 3, and that is positive. And my degree is 5, which is odd. And then I can see in my second equation, this is also not in standard form because I have like terms that I can combine. So I'll have a -3x to the 3rd plus 3x squared plus 8x. Remember to write them in descending order. Now I can see that my lead coefficient is -3, and that is negative. And 3 is my degree, which is odd. When we're describing the end behavior of a polynomial function, what we're asking is, what is happening as this function reaches off into the distance, as our function reaches negative infinity and positive infinity on the x scale? What is the y doing as we're stretching this out more and more and more? Well, if our lead coefficient is positive and our degree is even, then our function is going to be increasing on both sides. If our function is positive but odd, we will have a negative, decreasing y on the left side, and an increasing function on the right side. And if our degree is negative, or our coefficient is negative and our degree is even, we will have a decrease on both sides. And if our coefficient is negative and our degree is odd, then we will have an increase on the left and a decrease on the right. This is literally just what those arrows are doing that you see on your functions. So in example 5, we're asked to identify the function behavior and sketch what the graph might look like. I'm going to look at my function first to make sure it's in standard form. It is not. So I'm going to group my like terms right here and rewrite it in descending order. So I'll have 5x to the third plus 8x squared plus 15. My sign of lead coefficient is -5, which is negative. And my evenness degree is 3, which is odd. I'm going to look back up here, and I have a negative and an odd, and so that is going to look something like this. For my second one, I'm also going to look, and I see that it is not in standard form because it still has like terms. So this will be a 3x to the 8th plus 3x to the 3rd. My sign is 3. My sign of the leading coefficient is positive. And my degree is 8, which is even. And remember, the number of terms that we're going to have is equal to our degree. So we're going to have a positive even, which means they're both opening up. 1, 2, 3, 4, 5, 6, 7, 8. You can count them if you're not sure. And in our last example, we're asked to find what the possible function could be that represents this graph. Remember, you use we're going to number our changes of direction, pay attention to what arrows are going where. And then we also have this as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. So we can use this information to come up with some kind of function for these graphs. And I'm going to give you guys a chance to do that, and then you can fill it in. And so what I came up with is 2x to the 5th plus 3. And I use that because I see that my end behavior is a negative, or a decreasing and then an increasing. That means that my leading coefficient must be positive, and I know that my degree is 5 because I counted the turns in direction, and that must mean that my degree is odd. So I counted them, I have 5, so I use x to the 5th. Let's do the second one. And when I look at the direction that my end behavior is going in, I see an increase on the left and a decrease on the right. That tells me that my sign of lead coefficient is negative, and I count my degrees based on the direction. 1, 2, 3, which is 3. That is odd. So now I have a negative x to the 3rd minus 1. I hope you guys enjoyed this lesson. I'll see you next week.